So this is lab 2, which is motion of a falling object. Introduction, what is the problem? We're going to be studying the differences in an experimental model of an object falling, a computational model where gravity is the only acting force, and another computational model where both gravity and drag are acting as forces. Why are we interested in this answer? It's going to help us see if the drag force significantly affects a falling object. So a quick summary of our results. Accounting for drag force does make a slight difference in objects that fall slower than a rock, because it can slow the object's path. However, the difference is not large. So our fundamental principles include Newton's second law, which is initial velocity is equal to final velocity plus the net force divided by the mass times the change in time. So net force cannot be zero with a changing velocity. Our initial velocity is zero as it falls, but it heightens all the way up to a much larger final velocity, which means there must be forces acting. One of those forces is gravity, which is just mg. Another one of those forces is drag, which is that air resistance as it's falling. So the video that I use with Tracker is just a paper ball falling. You can see it right here. And it just drops all the way down. So I uploaded that into Tracker. And I received this graph right here of our y values. And this data of our y values as well. You can see the x values move a little bit, but we're really more focused on the y values. And so this computational model right here shows how I edited our code. I added our mass, our initial position 0, initial velocity 0, time 0. And over here is what we really changed. So the weight is equal to, as we stated earlier, negative mg times j hat, which is just that unit vector showing the direction. And that's our net force for this computational model. And then down here, we replaced ball velocity equal to Newton's second law. And over here, we use the position update formula. So let's go ahead and put these in, and this is the output that you get. Here's our graph, our position versus time graph that you get. And over here, I have our experiment right in blue and our computational model in red graphed together. And you can see there's some discrepancies that we're going to discuss later. But next, we're going to go ahead and include the drag force. So over here, F drag is negative b times the velocity. Negative b is a constant. We used trial and error to decide that it was going to be 0.0017. And our net force is now the weight plus the drag altogether. And down here, we also added our arrows, which is going to show us the differences. So right here, we got that drag force pointing up and that net force going down, that gravity force going down. You can see that obviously the net force is going to be pointing downwards still. That drag force is a super small arrow. So over here is our position versus time graph that we get from this model. And right here is our experiment modeled with this one. Now you can see there's slightly less discrepancies. Obviously there's still a big gap, but they don't cross down here like they did the first time, and it does follow the path fairly well. So let's discuss these discrepancies a little bit more. So that first graph, like I said, it ended up crossing, and this is because there was no upward force to balance out that gravity at all. So it does have a larger downward force, meaning it is going to go faster downwards. And the second graph does not cross, like I said, and it follows the path somewhat accurately. This is because we are showing the drag force, and this also shows us that the drag force, when it's included, can help make the graph slightly more accurate. But again, the difference is not huge. So let's talk about that what does it mean question. Well, when velocity is terminal, the drag force pointing upwards has balanced out the gravitational force that points downwards, meaning there is no net force and velocity is now constant. Let's take a look at our graphs and see if we see any terminal velocity. So here's that first computational model right here. And terminal velocity is going to go into a straight line because, like I said, velocity is constant and it's over here on that y-axis. You don't see any of that in this graph. Let's check the other one. Once again, no straight lines. That velocity is not constant at all. No terminal velocity is present here. So what if we had an initial velocity? So I went ahead and set the initial velocity to -5 the first time. And then I decided to just keep going up because we are more likely to get a terminal velocity with a much larger velocity. So I went all the way up to -1000, and this is what it produced. Right over here, you can see it starting to plateau, but it just does not quite reach that terminal velocity. So while it could be possible, it is incredibly difficult and unlikely to happen, and it would have to have an insanely large starting velocity. Yeah, and as you can see over here, there's another velocity versus time graph. So in conclusion, when drag force is accounted for, the position versus time graphs are more accurate between the computational and the experimental model. However, there is not a super large difference, and this is because drag force does not significantly affect these objects. So the end. Thank you so much for watching my video.